Alright, let's get started on the next problem. This is going to be LeetCode number 50, pow x of n. Implement pow x comma n, where x is raised to some power n, i.e. x to the n power. I think this is relatively straightforward to get a naive implementation going, but the main problem is going to be scaling it up so that it's fast enough. And that's where I'm not entirely sure whether or not I'll be able to figure something out. But we can cross that bridge when we get there. So in this case, it's relatively simple. So we can do the naive implementation of pow, which is multiplying x by itself n times. So for I in 0 to n minus 1. And we can say that if n is greater than 0, then we multiply by the amount. Otherwise, we divide by the amount. And we can also say if n is equal to 0, we can return 1, because anything to the 0th power is just 1. And then we also need to do a var current number is equal to x. And since we're starting at the first power, then we'll start this at 1, I believe. So let's say that we're doing 2 squared, so this would start at 2. Then for this one, this would run once from 1 to 2. No, 1 to 1, right? And this would run 1 time. And then we would do current number times equals x, else current number divided by equal to x, and then return current number. Because if we have a negative number, then we basically want to divide it by that amount n times. And yeah, this is a pretty straightforward naive implementation. Let's just go ahead and test it out to make sure that it actually works as expected. Looks like this needs to be a double, so let's do that. So again, relatively benign naive implementation. I'm just curious about oh, it looks like we did something wrong for negative number. Divided by equals to x. Interesting. Doesn't look like it worked at all, which is strange. If n is less, or if n is greater than 0, oh, math.absolute. Let's just wrap it in that, so we go n times, or n minus 1 times. There you go. So relatively straightforward naive implementation, but let's see how we can go further with this. We can keep that. We can just move this. So let's see. We know that for if x is exactly equal to 2, then we can left shift by n, or right shift. I think the main thing is just that we need to figure out, because if I recall correctly, for doubles or floating point numbers, assuming that this is IEEE 754, we have a sign bit, then we have the actual value bits, and then we have the exponent bits, and this is the number minus 127 or 128 is equal to the exponent, right? So the idea is that if we can get the exponent bits, then we can simply modify them to the value that we want. So the next question really then becomes, how do we turn a double into its bit representation? I'm not entirely sure if that's possible looking at the JDK, though maybe there's something within floats. Of course, floats and doubles are different, but I'm interested in sort of seeing whether or not there is a way of getting the bit the bit representation. Let's see. Minimum exponent, maximum exponent, number of bytes. Okay, we have this method, which is representation of the specified floating point value according to the IEEE 754 double format. So let's actually take a look at IEEE 754. Oops, sorry if I just bonked the microphone. So we have a sign bit and exponent bits and then the fraction. Okay. And the 64-bit layout is similar, where we have the exponent there, and then we have the fraction itself. Okay. So in that case, so the process is relatively simple, I think. So we start by turning the double into its string representation. Then we mask off the bits that we actually want to manipulate. And add the number of bits that we actually want. So I think the idea is that we could probably manipulate it so that we add in the exponent ourselves. And then we mask and then we or in everything else that we need. So we could probably do that with a string builder maybe. This is maybe a bit unconventional. There's probably a better way to do this. However, that might be what we could end up doing. So let's do val binary string is equal to x dot double to, let's see, this returns a long, and then we can turn it into a string. Is there a way? No, this is 11 bits. I was gonna say, can we use bytes instead, but no, I don't think so. So I think we could probably convert it into bits, into the long form bits, and then we do something different. Presentation, the doot, equals double to long bits. I think that's what we want. So we want to do double dot double to long bits x. Actually, since x is an object, I think we should be able to, right? I think we're allowed to do that. Double to long bits. So this gets us a long. Okay. I think we want that then. So this gets us our binary long. Huh. Double two long bits. Did I misspell it? No. Preserving. We should be able to get that. Unresolved reference double to long bits. Let me do double to raw long bits. Maybe that'll work. Interesting. Because this is a static method, it should be working. I'm not entirely sure why it's not. In any case, let's assume that that is the long that we want. And we can do a dot to string on that regarding double to long. And we don't actually need it to string it. We want to apply the bit manipulation on that, right? So let's see. We want to do, what do we actually want to do? Let's see, double precision. We want to preserve the sign. We want to preserve the fraction. We don't want to preserve the exponent, right? So the exponent is what we want to manipulate. And the exponent is what we want to modify. So exponent is equal to binary long, and let's see, 0x bit 63 is a sign. The exponent is this one. Thanks, Java documentation. So this masks off the exponent. And then we want to add, after we mask off that amount, we want to add the exponent n, right? We want to move it by n. Let's see. So what do we want to return? Well, we want to return, let's see. We're going to need to do a bit of shifting, and quite a bit of it actually. Let's see. If we wanted to move that, we want to preserve the sign. Well, what we could probably do is that we could do let's see, new number is equal to binary long, and we kind of want to negate we want to actually what I want to do is to negate the middle and then or that part back in. So if I wanted to negate that part, so that's 7, then F. So that would be 8, 0, 0. And then these are all F, I think. The idea is that we want to preserve within this, we have 3 bytes or 3 bits within the 3 bits within that section. 3 bits within there, so we want to preserve that. Actually, no, because each of these in hex represents a byte, right? So we want to actually do 1 followed by 3 zeros, which is 1, 2, 4, 8. Yeah, no, that's fine. Okay. Then we want to, these two F's are part of the exponent, so we want to get rid of those. Then we want to keep everything else the way they are, so we'll just AND ones, all of them. And then we want to OR this with our exponent. And then we can print this out and we can see what we get. And this will be long bits to double. Let's see if this actually is a valid method. I think Kotlin is a little bit weird when it comes to bitwise operations. Let me just double check. Yeah, it wants us to do this. Okay, value is out of range. And long bits to double is also not valid. Let's see. If we go back to basic types, numbers, double. Let's see. So it doesn't seem like we can actually use this double in the way that we actually want. Unless we just directly call it, but I don't think that, I don't remember if that's actually how we do it. It's been so long since I've really operated on the JVM. Yeah, no, doesn't look like that works either. And this component is out of range. Interesting. Let me go see if I can fix up these errors and then I'll be back. Okay, yeah, that's a pretty smart answer. So I took a look at the discussion page, and the idea is this thing called binary exponentiation. The core idea, I think, that needs to be understood is that any exponent in base 10 can be expressed as a product of exponents within base 2. That means that something like 7 to the 11 power can be expressed as 7 to the 8 times 7 to the 2 times 7 to the 1. So with that, we can sort of stay in this idea of base 2 and move a lot quicker than we could if we were just sticking to base 10 because of the ways that computers work in general. We'll also deal with our negative exponents by dealing with it in the beginning. So if our exponent is less than 0, then we will use the fraction 1 over x rather than x itself. And the same thing is that we need to transform our exponent left to its regular or absolute value form. We could use an math.abs there if we really wanted to. So from there, the algorithm is relatively simple. What we will do is that we will check our current exponent to see if the last bit is a 1. If it is a 1, then we will need to multiply our current value by whatever power of 2 we have currently there, right? So if we are at this 8 and our rightmost bit happens to be a 1, then we should multiply by 7 to the 8. Now, you may be wondering exactly how do we keep track of this if we're continuously shifting our exponent to the right? Well, with that, we just do a power of 2, and we keep a reference to basically our power of 2, and we will multiply this every single time. And since we're going in essentially right to left order, we don't really need to go back on any of our exponents. So we can just continue multiplying by our power of 2, and if there is a 1 that happens to be in that slot, then that's perfectly fine. We multiply it. And if there isn't, then we can just multiply it and skip that bit entirely. This way, the algorithm runs in logN time rather than linear time, where n is the exponent itself. And we achieve a little bit of a faster runtime that way. So let's go ahead and throw a submit on it. Looks like we ran into an error dealing with edge cases. Let's go ahead and quickly fix that. So if we have an n that is within those bounds, then we should probably shift it in a different way. Let's see. If we have that negative number. So we can also do some additional improvements. So we can say that if n is equal to 0, then we can return 1. Because we know that if the n is 0, then it really doesn't matter what the number is. We just return a 1. And we don't need to go through all that additional checks and conversion at the bottom. A very minor improvement there. We can also say that if our n it happens to be equal to, I think it's integer.min value, we can return 0. Because if we're going to go that low, then we've effectively reduced our values to 0. And likewise, I think we can say that if our integer is max value, we can return, I believe it's double.max value. I believe there is a max value here. Yep. And let's see. Well, it may not necessarily be max value, right? So let's just go ahead and run this and let's just make sure that it's working the way that it's supposed to. That seems to have worked. And then let's also throw this here. This, 6, right? Oh, it's 2 to this, let's see, it's 2 to the 31, or 30 minus 1, which is this instead, I believe. No, it's 2 to the 31 minus 1. Let's see. Well, what we could do is that we could do math.absolute value of n, which we coerce between double dot min exponent, double dot max exponent. And let's see if that actually solves kind of the issue that we want. I think it's coerced between. Could be wrong. In. Let's see if that gives us the values that we want. Min exponent doesn't seem to be... Did I spell exponent wrong? No. It seems to be... That seems to be correct. And this is part of the double class. Interesting. Interesting. Yeah, I'm not sure why this is not dealing with... This is not dealing with what we actually want. Let me take a little bit more time to work on this, and I'll be right back. Yeah, that was... Okay. One of the things that really tripped me up is really just this part right here. The idea is that we want to fill the areas that we shift with zeros. We do not want to preserve the sign in any way, because of the fact that we might be dealing with a large negative number like integer min value and something like that. We only care about the zeros, or we only care about the ones that are in the original form, so everything else can be filled with zeros. So when it comes to Kotlin, you should make sure to use the unsigned shift right rather than just the default shift right operation. Other than that, nothing else has really changed in here, and it seems like we've got a decent runtime and decent space. In any case, this took a little bit longer than I expected, but I hope you learned something, and I'll see you for the next problem.